So provide a multi-step synthesis for the following transformation of this alcohol to this diol with a long chain. And the clue here is that this is going to involve alpha carbon chemistry. Now it might be very apparent to you why this will involve alpha carbon chemistry, because you are taking chapter 21 right now. But when you're sitting in an exam, it is not going to be as apparent. So the clue is now going to be very useful in seeing how you can solve this problem more efficiently. Okay, so as you can see here, this is going to be, say for example, an aldehyde or a ketone, and then alpha beta, you have the other carboxy group in that beta position. So that's how you know that this is going to involve a Claisen condensation type reaction in one of the steps. Okay, so which means you have, if you want to have Claisen condensation, then you should have a carboxylic acid and then an ester. So oxidize this with the Jones reagent, say for example. Now that will give you the butanoic acid, OH. Treat this with thionyl chloride, SOCl2, and say for example an ethanol. That will give you the ester, and this is when you will use your Claisen step. So 2 molecules of this treated with sodium ethoxide, what happens is, so you will generate your enolate on one of the esters, and that is going to attack that carbon center, opens that up, and when the oxide comes back in, this ethoxy group is going to leave. So you are going to get your Claisen product there. So let's make sure we number it properly so we understand how this works. So 1, 2, 3, 4, and that carbon is that carbon, and this is one, say let's say A, B, C, D, that is A, B, C, D. Okay, that is your Claisen product. Now after this, how do you get the final product? You can simply treat this with lithium aluminum hydride followed by acid workup. Okay, so the ketone is going to be reduced to the alcohol. So if you want to label this here, that is 1, 2, 3, 4. So that carbon here is that carbon which reduces to the alcohol, and this is your other chain, which is A, B, C, D. Okay, which is that chain over there. Okay, so that's that. Now one thing that you want to keep in mind is it is very important to make sure that you use lithium aluminum hydride here. And if you think about reducing it, if you think about hydrolyzing the ester first to a carboxylic acid and then reduce it in a second step, and think that there is nothing wrong in that, there actually might be a problem, because if you treat this with acidified water and you heat it, what will happen is the ketone will stay intact, of course, and you'll hydrolyze your ester to a carboxylic acid. But since you have a carboxylic acid, what will happen is since you have a beta keto carboxylic acid, you have the risk of decarboxylating this and getting 1, 2, 3, 4, 1, 2, 3, 4, getting this molecule here. Okay, because when you have the beta keto carboxylic acid, that is going to undergo decarboxylation. So therefore you have to be careful not to do this, and if you want to get this final product, simply reduce it with lithium aluminum hydride. Now that being said, if you are careful and you don't heat this reaction, you can have a stable carboxylic acid there, and then treat this with lithium aluminum hydride again, and that will give you the final product. Okay, so that's essentially what it is. So this is the best way to make sure you don't have the trouble of losing the carboxylic acid.